e to the I k pi dollar, right? So this is the either the going in forward scalar or backward scalar rate that you have. And generically, what the physicists do normally is to take a operator, right? People may heard about this word operator, some sort of operator would transform the incoming wave to the scalar wave like this. And this is called a transformation matrix. And so a lot of the work then is to calculate what is the matrix element of this transformation matrix, which contain, of course, the potential that you have. So it's scattering off electrostatic potential. So all the physics is in here in this fuzzy operator, which you have to define mathematically what this transformation matrix is. So schematically, we can understand as chemists that really you have in and out, right? So you have wave coming in, wave coming out, and in between is an operator which transforms this incoming wave to outgoing wave, right? So logistically, it's quite easy to understand, but of course, in detail, this transformation matrix is very complicated. And a lot of work has been going on to try to do this calculation, to generate cross-section like this. Okay, then we talked about a little bit last day about limitation of the information content on lead. One of the things that I mentioned about is that there are two things. The things that we talked about so far is of course the pattern recognition. So you have diffraction spot, and that corresponds to reciprocal space. And we haven't talked so far about actually measure the intensity of these spots. We'll talk about it shortly. So we have this pattern recognition, and so there's limitation on just looking at the lead pattern. Okay, so keyword pattern here. The problem is that we can get a real space to generate a residual space, but to go from residual space back to real space, that's not a one-to-one correspondence. In other words, if you give me a residual space pattern, I can give you many possible real space patterns that can give you that residual space pattern. Okay, so it's not a direct one-to-one correspondence, and that leads to ambiguity. Okay, so one of the example I used last time is let's say in the residual space I see something called 2x2 pattern, which means that in the lattice vector the absorbate, I'm using the target absorbate, absorb every 2 units, right? Every 2 units in the vector. So all the circle one are the absorbate, right? And sorry, you got it out here. So all the black dot, right? All the black dots are the strong points, are the strong intensity points in residual space, and they correspond to the substrate. The weak point occur in between. Okay, so you basically have in residual space, if you have something twice as long as real space, in residual space it should be half as long. So here you have a vector that's half as long as the substrate one. So here for the solid dot, you have one length. The open dot is correspond to your overlay, which is half as long as the solid dot ones. Okay? So this weaker spot, which I represent by open circle, are known as the overlay or absorbate spot that you have. Okay? So you can see this on a lead pattern. You will see strong spot, set of strong spot, and set of an overlay on top of this strong spot is the tiny weak spot, depending on how intense, how much absorbate you have. Okay. So this is known as fractional spot. There's a lower fractional spot in lead terminology. And what I'm saying is that here, so here you can go back and you can say, well, because I know that this is a 2x2, it means that in real space, my overlay atom should be twice as long. The unit vector should be twice as long as my substrate. So here is a representation, if you like, a representation of a possible geometry that you got. So here you have the substrate represented by a circle, and then where the absorbent will hit will be this one, this one, this one, and this one, like this, right? Because every other spot, every twice distance, right, is one length, and then twice the length, will be my absorbate, which corresponds to my fraction of 1/2 spot. Okay, so that's a 2 by 2. Now, it is not possible to separate this 2 by 2, what I observe on a lead optics, from something that I have free domain of a 2 by 1. In other words, I can have a domain. This is a real space here. This is a real space here. One of them, the absorbate absorbed in this way. Okay, along one direction, I have twice the unit. In this direction, I have the same length as the substrate. That's one way. And the other way is that in the opposite, in the other direction, which is this direction, right? So that will give me a 2 by 1 and then 1 by 2 spot, and then finally I have the third direction because this is a hexagonal type symmetry like this. So essentially I have 3 different domains. These are called 3 different domains. Domain are jargon that used by material chemists that correspond. A domain is something that you have the same crystal structure. Okay, so this is one domain, second domain, and third domain, and they are arranged in a certain way. And if you sum all 3 domains together, you will generate a residual space that looks exactly like a 2 by 2. So in other words, if you have just see a 2 by 2 pattern, you cannot tell whether you got this or 3 separate domains of different 3 separate type of domain overlapping each other as examined by the Bianchi. Okay, so these correspond the little weak spot here, the triangle and the square and so forth correspond to each of these domains, and they just overlap the lead pattern. Each of these generate a diffraction pattern, and they all overlap into the same, and this is what you observe. So you cannot tell from this one versus this one, and correspondingly you cannot tell the lead of the corresponding real space pattern that you should get to generate the residual space one that you see. Okay, so there's an ambiguity associated with this, and here is, and I said down here, I'll ignore this, I said down here that this due to the present domain and anti-phase domain boundary complicated thing. So this is what we had talked about last day, is that this is one domain, and this is so-called an anti-phase domain. Basically, an anti-phase domain is something that just missed an atom, right? So you have the periodicity, you just consider this, is exactly the same as this. But they don't, but at a certain break boundary point, there's a break in periodicity between the two. They don't go in the right order. So this is an anti-phase boundary between 2 domains. Okay? So that's the problem, that you have this anti-phase domain that could lead to interesting results that you have. Now the other thing that I mentioned here is that the lead pattern is not sensitive to local structure. By that I mean that if I put my atoms, right, we put my absorbing atom on a 4-fold hollow site, right? This is my substrate. The solid line is my substrate atom, and then the crosses are my overlay atom. So this is known as 4-fold hollow because it's got 4-fold symmetry. I cannot tell from the lead pattern generated from this versus a lead pattern generated if I move my absorbate to a bridge site. But the arrangement is still the same. You see, the arrangement is still unicell-wise still the same. It's just the local structure changed. Instead of 4-fold hollow site, I have a bridge site, right? And by the same token, I can also put it on another bridge site, right? So here you have one direction bridge site, and this is a second bridge site on here. And all 3 of these will generate exactly the same